Hi, welcome to my talk, Lowering XLA HLO using RISE, a functional pattern-based dialect. I'm Martin Lücke, a second-year PhD student at the University of Edinburgh, and let's have a look at how we represent computations in the functional RISE dialect. So here we have the example of a matrix-matrix multiplication, and to compute the yellow output element of matrix C, we perform a dot product of all the values, the green values in the row of A and all the red values in the column of B. This means to compute the full matrix multiplication, we have to compute the dot product for all rows in A with all the corresponding columns of B. And when we look at the RISE program above, we see that this is exactly how this program is written. So the map pattern, which is highlighted in green, applies a function to all elements of an array. And as a matrix is just an array of rows, this applies a function to all rows of A. So for all rows of A, we do the following. And next, again, we have a map pattern, which is highlighted in red and is applied to B transposed. So we do the following for all columns of B. So in an imperative sense, this means for all rows in A, for all columns of B, we compute what's in this blue box. And in this blue box is the dot product represented in RISE. And this computes our matrix multiplication. And one of the main things you should note here is that the matrix multiplication is actually built out of the dot product by composition. This means when we have an optimization for the dot product, it automatically applies to the matrix multiplication as well. So this lightning talk is about how we lower a representation such as XLA HLO using RISE. So let's say we start with a machine learning model such as MNIST for handwritten number classification in TensorFlow, and we want to compile and execute it on a given hardware. And while doing this, we want to leverage the advantages of the functional pattern-based representation. So the first step in our approach is lowering the TensorFlow model to the XLA HLO MLIR dialect. And here on the left-hand side, you see a shortened version of this MNIST model in this dialect. And here we match for supported operations, for example, matrix multiplications or convolutions. And in this particular example, we find two dots, so matrix multiplications in this case, and replace them with the corresponding RISE operations on the right-hand side, which is exactly the matrix multiplication we've just seen. And in consequence, after these steps, the operations that we are interested in are all represented in the RISE dialect. So in this compilation flow, we now have a way to lower our machine learning model down to RISE. So we have a blue arrow. And the natural next step is lowering the RISE dialect. And for this purpose, we use the existing affine and standard MLIR dialects, which provide, for example, the notion of loops or loading and storing data. And so here on the left-hand side, we see the same matrix multiplication as before, now represented in the actual RISE dialect. And on the right-hand side, we see the same computation in the affine and standard dialects. So we see the three loops and the usual access and computation structures of a textbook matrix-matrix multiplication. And we want to lower the left functional pattern-based representation to the target representation on the right-hand side. So let's shift the target representation to the right for a second, because our approach is a two-step process. And the first step is lowering the functional representation on the left-hand side to an imperative representation in the middle. This means on the left-hand side, we have functional patterns like map and zip and reduce. And on the right, in the middle, they have been lowered to loops, indexing computations, and assignments. And here I colored the pattern, and the code is lowered to in the same color. So for instance, the reduce pattern is highlighted in yellow, and in the middle we see the reduction loop, the reduction for loop, also highlighted in yellow. And the second part of this process is lowering the imperative representation in the middle to the target representation, which is affine and standard. So we start already in the imperative world and perform this lowering by resolving all indexings and finish up by generating all necessary load and store operations. For instance, the blue multiplication depends on two values from matrix A and B, which we have to load before the computation. These are highlighted in green on the right-hand side. And now we can use the existing lowering infrastructure in MLIR to lower to LLVM for execution. So in conclusion, we now have an end-to-end system where the input is a model from TensorFlow, and we compile it by progressively lowering it using the MLIR infrastructure, including the RISE dialect. Okay, so today we have a high-level functional pattern-based representation, RISE and MLIR, and an end-to-end lowering flow from XLA HLO via RISE to LLVM. And we have shown in prior academic work, for example LIFT, that this representation is very beneficial to perform high-level optimizations in a principled way via high-level rewriting. So the next step for us is implementing a composable rewrite system in MLIR based on our current ICFP paper. Okay, thank you very much for listening. All the work you've seen today is open source on GitHub, and I'm very keen to hear comments.